One small step is one giant leap for humankind. And this partnership will take us one step closer as we dare to explore the unknown. Let us dare to ignite the future farther, faster, together. Congratulations to both NASA and DARPA on this exciting investment in the future of human space exploration.
I welcome you. I'm Steve Howe. I welcome you to the new collaboration to advance propulsion technology session. I was 25 years at the Los Alamos National Laboratory and 10 years as director of the Center for Space Nuclear Research at the Idaho National Laboratory, and currently working for my son at Howe Industries in Phoenix, Arizona, part-time. I just wanted to mention how I first got introduced to nuclear thermal rockets. In 1982, ex-senator and Apollo lunar astronaut Harrison Schmitt approached the director of the Los Alamos National Laboratory and instigated a joint study between NASA and Los Alamos over 6 months to identify all of the issues of a human mission to Mars, what it would take. And I was the co-chair of the Los Alamos team, and my specific task was to look at using an NTR, nuclear thermal rocket, and how it might benefit the mission to Mars at the time, and then to identify the issues necessary to recover the technology. So as Administrator Nelson mentioned, in 1957, Los Alamos was given the task of the rover program, which was to design a nuclear reactor with an appropriate fuel that could reach about 2,500 degrees Kelvin, and design the reactor part. In 1963, the Aerojet Westinghouse team was awarded the NERVA program, Nuclear Engine for Rocket Vehicle Application, to make that into an engine. So from 57 to 72, they tested 23 different reactor engine prototypes, all the way to TRL 6+. They even had a test stand with a reduced, steam-driven reduced atmosphere. The largest test during this program was the Phoebus 2A at 4.5 gigawatts, 250,000 pounds of thrust. The smallest engine was the Pee-wee, which was late in the program, at 500 megawatts and 25,000 pounds of thrust. Both of them had measured specific impulses of 850 seconds, which is almost twice that of the LOX hydrogen main engines on the shuttle. So the potential benefit was tremendous for a factor of 2 of ISP. The programs ended, both of them, in 1972 when the country decided to no longer travel to the moon. And it ended there. Several of us have tried over the years to revive and pursue the research and keep the technology alive, if you will. As we just heard from Administrator Nelson, the U.S. is now interested in expanding operations in cislunar space, going back to the moon, maybe going on to Mars. Over the last few decades, several National Research Council studies have done comparisons of propulsion systems and almost always concluded that the NTR was certainly mission enhancing and sometimes mission enabling for some of these missions.
With the demonstration rocket for Agile Cislunar Operations, or DRACO, it's got really big implications for NASA's Moon to Mars work. As the administrator referenced, we have a Moon to Mars strategy, and we have objectives that we've been working on now and in the coming years to achieve our big goal. So our intent is to lead and develop a blueprint for human exploration and sustained presence throughout the solar system. That is a very important goal, and we think that these advanced technologies will be a critical part of it. Within our objectives buckets, we have several buckets that include science, infrastructure, operations, and then, of course, transportation and habitation, because you got to get there and stay alive while you're doing it. And DRACO will be a critical part of evaluating the technologies that will take us deeper into the solar system. And by the way, Steve, there's no might. We're going to Mars. So we do know that we need to be evaluating options for power and propulsion. As Steve referenced, that is absolutely critical for us because of the risk to the crew. And I'll talk a little bit more about that. The key thing, of course, is, as both Steve and the administrator mentioned, nuclear thermal does have high thrust to weight similar to chemical, but it's 2 to 5 times as efficient. So these propulsive capabilities will enable the U.S. to enhance its interests in space and to expand the possibilities for the future, supporting NASA's long-duration human missions, but potentially also our scientific missions as well. So this is really a tangible step forward for us in getting humans to Mars and our deep space exploration. The key thing is that this will allow us to evaluate the opportunity to move faster. If we have swifter trips for humans, they are safer trips because of the incredibly harsh radiation environment that humans have to endure going all the way to Mars and in other deep space destinations. So the ability to go faster can make a huge difference for the safety of our crews. So as I mentioned, this also has the potential to extend into creative science missions that are not possible today. In the future, we really hope to have more scientists going to do studies in situ, and we need those scientists in residence, not just on the moon, but also Mars. So anything, of course, that we do like this also has an enormous impact on our aerospace base.
So for the last 65 years-ish, DARPA has held steady to the mission that started way back at the beginning, which was to both prevent that type of technological surprise and to create it ourselves. And we typically do that by making pivotal investments in breakthrough technologies relative to national security. So our role is to take the technology excuse off the table for doing that next great leap ahead thing. So NTR technology then aligns with that mission. Holds a lot of promise, as you've already heard multiple times, in terms of more efficient ways of traveling to Mars. And also, for a lot of us, when we think about the future of space, just providing the maneuverability necessary to give space leadership options. So when you think about national security, maneuverability is actually one of the things that everybody operating in air, on land, on sea, undersea, really, really prizes. And it's a capability that we don't have enough of yet in the space environment, and it's one that we aim to be able to prove is at least possible to make that another option for commercial leadership and for basically the future of economics in space. For those of you familiar with the history of nuclear engine development, which is probably a much larger percentage of you than in the average audience, it's important to point out how our technology is actually new. So as Steve mentioned, a lot of really groundbreaking work in NTR technology has already been done. Hasn't been done in space. And one of the key enablers that lets us sort of go forward today, which might not have been possible even a few years ago, is the ability to use a different type of fuel. So rather than using highly enriched uranium, we're taking advantage of the ability of using high assay low enriched uranium, or HALEU, which is part of this whole burgeoning economic explosion in nuclear energy, and particularly in small reactors. So it's an exciting opportunity space for us. That ripple effect, allowed obviously changes in space policy and lets us go forward with taking some risks that might not have been possible not too long ago. Or you've already heard enough, I think, about NTR propulsion and what it offers. The bottom line is that we are a spacefaring nation, and ever more and more part of a spacefaring planet. So operating in space is important to scientific discovery. It's ever increasingly more important to modern commerce, as well as to national security. I want to thank our partners in the U.S. Space Force. They've signaled their support for DRACO with the intent to provide us launch support when it's time to do the demonstration. So,
with this ISP, right? So is there an application for some lunar missions that NTR is applicable to?
I think there absolutely could be. One thing that we have certainly learned from operating the International Space Station is humans and science take a lot of logistics. And so being able to get things back and forth is very important. In some cases, the slow boat from China is absolutely fine. I don't know if that's, you know, it's a saying anymore. It was when I was a kid. But, you know, the very slow, that can be very useful for certain mechanisms. But it isn't ideal, especially for humans or for high interest or, you know, high capacity cargo that we're trying to take care of. So we do think that there is the potential. We'd love to see commercial spin-offs come after a successful tech demo that may enhance our ability. But of course, a huge part of this is the blueprint for sustained human presence and exploration. We think those trades are also going to be out there between chemical, electric, nuclear electric, and nuclear thermal. We need to be doing these tech demonstrations now to prepare ourselves for an analysis of alternatives in the early 2030s for a Mars transport vehicle. So that's really what this is about.
We know the Russians put 30-some reactors up in space. They were small, 10 kilowatts. We had one reactor, the SNAP-10A, in '64, but the U.S. hasn't launched a reactor. We've launched RTGs and space batteries. Was there a problem in regulatory approval? Is this a big hurdle? Do you think this is, you guys have got a big burden here trying to get this launched. Pam, we'll let you start.
Yeah, I think probably the biggest hurdle for regulatory has actually been with commercial, and HALEU is absolutely going to help that. SPD 6, the Space Policy Directive 6 from the White House, provided a lot of clarity in this area. I think the government has always been capable of doing what it wanted to do, if to find the authorities to do it. But I think the clarity of the agreement between DARPA and DOE, where DARPA has the oversight authority, is absolutely going to make this move faster. So I think there's a lot of different pieces that came together in that policy environment. But for me, the really big outcome is using HALEU is going to streamline a lot of that because it's not considered weapons grade material. And so that means also the potential for commercial spin-off is there.
Excellent, very good. So safety. I mean, obviously the public's going to say, you're going to put a reactor over my head. You want to talk about, Stephanie, a little bit about the safety for launch operations and operations in space?
Absolutely. You know, I have a colleague who likes to refer to the times decades ago before safety was invented. I will tell you safety has been invented, and we're putting a lot of time thinking into that. Our amazing program manager for this project has been sort of living and breathing a lot of the safety considerations. So, you know, for example, the system is essentially going to be designed so that there is no way to actually get the engine going until we're fully on orbit. And we have a lot of safety measures built in for any kind of an accidental launch failure or things like that. It's just embedded in the entire culture. The rocket is designed to basically stay in space in an orbit that would not degrade until well past the lifetime of the actual fission materials. So it's just sort of embedded in the entire design process. So
good, excellent.
Very, very important.
Essentially no risk, no risk to the biosphere.
Yeah.
So along this, in the original days of Rover NERVA, there was a joint program office between AEC and NASA, Atomic Energy Commission. And can you talk a little bit about how this is going to work, this collaboration? Pam, are you having a joint office? Are you sharing offices? How is NASA going to work with DARPA to do this?
Well, part of it is to, we've been focused on structuring with kind of clear lines of responsibility. NASA will be working on the engine itself, basically, the rocket engine and the reactor part, and that allows us to kind of make sure that we've got. I think this is really important whenever you set up a joint effort like this: who's doing what and who has responsibility for what. The good news is that we have been partnering with DARPA on through the DRACO program from the beginning. At the program office level. So yes, we have a program office at NASA that is dedicated to all things nuclear, and they'll be working closely with the DRACO program team. Do you have anything to add?
Yeah, I think that, you know, often those That structure evolves through the life of the program, and what you need sort of in the first phase when you're doing exploratory designs versus what you're doing when you're getting ready to launch will vary. I think the bottom line is we have really strong communication, people that respect and trust each other, and they will adapt as needed. And of course, there are other partners as well. So the Department of Energy, Pam mentioned that they have authorized DARPA to take responsibility for this overall project, and they will be acting in an advisory capacity when we need it, given all of their expertise in nuclear power and things like that. And of course, the Space Force will become a little bit more of a role as we get closer to actual launch. So
I'll just add to that, in my experience with joint offices, one of the things that's really critical to make it work is that you have the support all the way at the top of the agency and positive relationships. And we couldn't have a better relationship. Yeah. So that helps a lot when you have things you have to work through.
So it's not on the list, but I'm going to ask you anyway. Funding. Do you have congressional support for this? I'll let either one of you take it.
Yeah. Oh, absolutely.
Okay.
We have it built into our budget for the full duration of the project.
Excellent.
Obviously, we are counting on mission partners for certain parts as we go forward, but those commitments are very positive.
Certainly, we have in the 23 enacted $110 million in this area. And of course, we will continue to submit budget requests that will support this activity. One thing that's kind of nice is that everybody loves a joint project. Because, the sense of our congressional committees and even OMB examiners is that we're, getting more bang for the buck. So that is helpful.
So Pam, just a couple of minutes then, if you want to elaborate, what's the difference between a chemical engine and a nuclear engine, just at a high level? What's the fundamental?
Well, there's a couple of key things. So for nuclear thermal, you do have a hydrogen tank. For if you had a traditional rocket, you would have to have two tanks. You'd have to have a fuel and an oxidizer. So in this case, the hydrogen is actually pumped into the reactor with a turbo pump that looks actually pretty much like a traditional rocket turbo pump. And then it's heated up and it's ejected out of the nozzle. But the fact that you're not carrying two, both the fuel and the oxidizer certainly provides some efficiencies. You talked about ISP, some of those things that make it more efficient. So there's, potential for mass savings in the end. So it's just, like, as you pointed out, very, very high ISP.
Are you collaborating with private companies, or do you plan to do so on this?
Oh, absolutely. So again, for those that aren't familiar with DARPA, we don't have internal labs. We don't do our own work. We get the crazy idea, and then we convince other organizations to actually do that scientific technical work. So we're in the process of evaluating proposals right now, and in a couple of months, you'll hear more specifically about who will actually be doing a lot of this, the next stage of DRACO work. Sure. And well, as Pam has mentioned, when you start to get into highly enriched uranium, you get into significantly more safety areas that you have to pay attention to. There are more regulatory issues. You're starting to move closer to weapons grade material, all kinds of reasons, both technical and sort of societal, that affect how flexibly we would be able to do a program like this. So the availability of the high assay low enriched uranium sort of changes the game. So we're talking about sort of 5 to 20% enrichment, whereas with highly enriched uranium, you could be talking up to 90%. So it's a significant difference in the space that we're working in. It's also, as I mentioned, I think DOE is really, really embedded in this. It is a significant part of the future of portable nuclear power, and so it is something that they are very focused on. We're focusing on it for space, but it is actually an enabler for nuclear power, ground-based, sea-based, wherever else you would potentially want to use it.
Now, you're planning for a 2027 launch. Nice and ambitious, DARPA hard, kind of a mission.
DARPA scary.
Yeah. Do you want to talk a little bit about altitude? How high is it going to be? Is it going to impact space station? Do you have to kind of time it right? Anything like that as far as the first test? Pam, do you want to
No, I think Stephanie mentioned that it's critically important for us to get to a high enough altitude that that the material will no longer be radioactive by the time it re-enters.
Right.
And so that's critical for us. So that's sort of a minimum at the 700 kilometer threshold, and maybe up to as high as 2,000 kilometers, both of which are well above the International Space Station.
Okay.
So
there's no issue being
300
close.
years plus for re-entry. So.
And again, I'm going to go off target here. Any radioactivity coming out of the exhaust? Are we putting anything into orbit that could last a while? Either of you want to take it, or?
So, I mean, I think it's just worth reiterating that part, that obviously we are putting radioactive materials into space, but we have designed the entire process to be safe, right?
Right.
So that part of the reason of doing it in space, in a lot of ways, it's safer than having to do it on Earth.
And what comes out of the rocket engine is gaseous hydrogen.
Right. Exactly.
So, yeah.
I just want to emphasize
Yep,
that.
yep.
It's not
gaseous
radioactive.
hydrogen. Yep. Which you can find a lot of in space.
Okay, we have a question that I think you both covered, but we'll hit it again. After DRACO is successful, what do you expect the role of NTRs to be in the space domain? I think you've both kind of covered this from your own respective issues, but well, let's ask it a little bit differently. What's after DRACO? What's after the first test? You pop the bubble regulatory, you put a reactor up in space, first time in 60 years. That's the big step. What's next? What's the next step after that?
Well, I'll start, because the longer and more profound answer is going to come from NASA. Because DARPA's role, we have a very short attention span. If we are successful, once we have proven this is possible, we will move on to something else, right? This is sort of the nature of DARPA, is we rotate our people, we're having them bring in these crazy ideas, and then we're taking the risks to demonstrate that they're possible, and then we're moving on. So it is most likely that once we have, if we're successful and we have taken this technology excuse off the table, then the idea is to help transition that to other parts of the U.S. government. NASA already has a very clear plan, and as we said, we're talking to the Space Force so that they can add that to the options that they can explore for what comes next for them.
Okay.
Well, if I could riff for a minute on what makes NASA different than DARPA, I think it's one of the things that's really fun is that we both are, our mission is to explore the unknown in air and space. And to do that, we have different mission directorates that work on aeronautics technology, that work on space technology, so cutting edge development. But we also have operational missions, right? So both for science and for human spaceflight. And so we are both a tech developer and also the transition partner, like take that tech and go actually do something operational with it, which is really fun to partner with DARPA, because we have that DNA in our space technology mission directorate that's about tech demo and tech development, but we also have an in-house built-in transition partner. Does it make it easier? I don't know, but it is different. I know that one of the hardest things at DARPA is once you've demonstrated it, really encouraging the use of it and operationally finding that transition partner. So, from my standpoint, I just wanted to point out that that's one of the different things about the way NASA works. We do think that there is the potential for commercial spin-offs to be useful in Cislunar. That is the scale of DRACO. It's really designed for cislunar operations. We do think that if we're successful, we will have to take one more step to look at the scale that we will need for a Mars transport vehicle, which is going to require some scaling of the technology. Probably less risky step, but also critically important, again, to that analysis of alternatives in the early 2030s.
Excellent. They appear to be a little bit concerned of the joint effort and meeting the date. So are you working, have you developed new ways of working together? Because usually when you get more chiefs in the kitchen, things often delay a little bit. So have you come up with any kind of something on new structure or new program management, or how do you think this is all going to just blend together and meet that 27 date?
So, I think Pam mentioned this. One of the best things when you're creating a complex organization is to have very clear lines of responsibility. So, what people might be concerned about a joint design approach, you're not this is not a free-for-all, right? Everyone understands what components they're responsible for, and clean lines of communication matter. So this is actually not that new, I think, for either of our organizations, and it's something that I think we both have a lot of confidence in. So we haven't invented new program management structures. We're pretty confident that what we're working with will be.
And this is the DARPA program.
Yeah.
It is the DRACO program, and so DARPA will take leadership in most of those key areas, especially the safety responsibilities. Not that we won't be supporting in every possible way, but I think we're all really clear on that.
Yeah. It's also worth mentioning our goals are not, in conflict, right? We are very much looking for the same thing. And so that helps too. So I know people probably think of stories where you've had organizations that were trying to take advantage of some overlap in interest. We have very, very well aligned interests, and I think that's a huge accelerator for making this work.
I have made the claim recently that you guys have accomplished more in the past 3 years than I saw in 40. We kept pushing the Sisyphean rock up the hill and never getting there. So how's the landscape changed that has enabled this to now start to be considered? So Pam, why don't you go first, and then we'll wrap up.
Well, I mentioned SPD 6, which was very, very important in the last administration. I think technology capabilities, certainly the onset of HALU has made people say, hey, some of these key barriers we're knocking down. I think there's also sort of a cultural barrier that we have finally gotten to the point where we've overcome. As you look at the clean energy transition, people are more sophisticated and understand that nuclear power is one tool in the toolkit for us to be considering. And so I think it's kind of gained broader acceptance that nuclear power has a place here on Earth as a part of our energy portfolio. And that's actually important too, because there's perceptions here that also have impacted that. But I think a lot of different things have sort of come together at just the right time, which is fun.
Exactly. I couldn't have said it better. I mean, I can also throw in there that obviously in almost any technology space, we have been being able to take advantage of the opportunities in computational improvements, in new materials, things like that have all kind of moved forward. But what Pam mentioned, some of these like barriers to entry that kind of sort of faded away kind of all at once, really opened up the door for being able to be able to take this risk and try something that intellectually I think people were prepared for quite a while. But you need that perfect storm of everything aligned in order to really take off. So.
I might pick up on the one tidbit you touched on, and that is if you think about rover Nerva in the 60s, there wasn't much of a computer to be had. They went from concept to test in 18 months. Now they had Senator Clinton P. Anderson to help them, and they had a budget that was unimaginable. But now we've got so much computational modeling, and we can do so much pre-work before the testing, that I think that's what makes this, that is a landscape change in a sense, from the old days. I think that's exactly right. I would just like to entreat all of the young people in this audience and all of the people that have worked for years pushing nuclear thermal rockets. I think now's the time. Support this in any way we can, and I look forward to seeing this fly in 2027. That's going to be pretty exciting. With that, I'd like to thank Pam and Stephanie again for an excellent discussion, and wish you all a good day. Thank you.